Visible? Abhinav? So another method was impulse invariance method for converting the analog filter to digital filter, or converting the transfer function or impulse response HS to HZ. Okay. So means once one filter is given, generally that is given in analog transfer function form. Now when you design the digital filter, you have to convert the analog transfer function into digital transfer function. So HS should be converted to HZ. Okay. So there are many methods. These are very important methods like impulse invariance method, then bilinear transformation. Okay, all we are going to see this. Now we discuss. We have already started. One method was there, that is approximate that using difference. What is that method? That is approximation of derivative methods. That is slightly less important. And but this method, impulse invariance method, is very important. See, let us start with one transfer function Hn, okay, that is uh, in discrete domain, okay, Hn. So and we have analog transfer function, okay, that is Hat. Okay, so that is the impulse response for analog filter. Impulse response for analog filter Hat, and if it is digital filter, it will be Hn. Okay. So now if you sample the impulse response, okay, by at nt instance with sampling interval t, then Hn can be written as Ha of nt, okay, where t is the sampling interval. Now the Z transform of impulse response Hn is Hz. Okay. So summation n is equal to 0 to infinity h of n z to the power minus n. Now we know the relation between the Laplace transform and Z transform, that is Z is equal to e to the power st. Okay. So when so s is equal to sigma plus j omega, we know, and z is equal to e to the power st, that gives you the relation between Laplace transform and Z transform. So we replace Z by e to the power st. So we get the equation, this equation, summation h of n into e to the power minus stn. Okay. In place of Z, we write e to the power st. Now, what is the effect when uh, we go from one plane to another plane, that is S plane to Z plane? What is the effect? So S is what? S is equal to sigma plus j omega. Okay, that is the points in the S plane. Okay. So, and at the same time, Z, you know, it is equal to e to the power st. Okay. And also Z is equal to e to the r into e to the power j omega. That is a complex variable. So that determines the points in Z plane, different points in Z plane. That is applicable for digital filter. And S is what? It is the applicable for analog filter. We want to relate the analog filter to digital filter. So uh, in place of e to the power st, okay, we write in place of s, we write sigma plus j omega. So it would be e to the power sigma plus j omega whole into t. That means e to the power sigma t into e to the power j omega t. E to the power sigma t into e to the power j omega t. And z is equal to r into e to the power j omega. These are the points in S plane, a Z plane. And so left hand side equations is points in, represents points in Z plane, and right hand side of the equations are the points in S plane. Now we see some uh, characteristics. We find some uh, relations that if sigma is less than 0, okay, so S plane is what? S plane is the plot of different points with axis sigma, x axis sigma, and y axis j omega. So sigma, if sigma is less than 0, that means it is left half S plane. If sigma is greater than 0, that means right half S plane. If sigma is equal to 0, that means it is only what? It is the j omega axis of the S plane. So how all the points are of S plane, that is left points on left half S plane, points on right half S plane, and the points on j omega axis are mapped, okay, are mapped to the Z plane. And we know that Z plane is what? It is a circle of radius r, okay, and where the phase or the vector rotates with speed omega. Okay. Omega is the frequency, pi radian per second, omega radian per second. That is the frequency. So R is equal to, we can say that R is equal to, with this relation, R is equal to what? E to the power sigma t, and e to the power j omega is what? E to the power j omega t. So here omega is small in the Z plane, and in the S plane omega is capital, denoting analog frequency capital omega, and small omega is the digital frequency. So we can relate that this omega is equal to small omega is capital omega into t, or digital frequency is f by fs. Okay, you know that digital frequency can be related as f by fs, where f is the f is the continuous frequency, and t is the sampling interval or reciprocal of sampling frequency 1 by fs. So if now from this relation, if sigma is less than 0, what happens? If sigma is less than 0, and since E is greater than 1, that is in between 2 and 3, so power of 2 with fraction means that it is less than 1. Okay, it is less than 1. So R, that radius will be in between 0 to 1, or the points, that is left half S plane, that is sigma less than 0, these points are within the unit circle. Similarly, sigma greater than 0, that means e to the power some value greater than 0, okay, that is some positive value. Okay, so 2 to the power uh, 2 to the power something value, so it will give you the r, that is radius greater than 1. So and at the same time another case sigma is 0 means r is equal to 1, e to the power 0, that is r is equal to 1. So there are three cases of sigma, that is sigma less than 0, okay, that is e to the power some negative value, that means 1 by something, okay, 1 by something to the power negative value. There is 1 by 2 to the power something. So it is what? It is less than 1. Okay. So sigma less than 0 corresponds to left half S plane. Sigma greater than 0 corresponds to right half S plane. So all the points lying in the left half S plane are mapped within the unit circle in the Z plane, and the points lying right hand side of the S plane are outside the unit circle, and the points on the j omega axis, that is sigma is equal to 0, are lying on the unit circle. Is it clear? As usual. So this thing is explained here, that the left half plane in S domain is mapped inside the unit circle in Z, and the right half plane in S is mapped outside the unit circle in Z, and also the j omega axis is mapped onto the unit circle in Z as indicated above. Now next, another concept is that if we map the j omega axis, okay, j omega axis on the unit circle, okay, so what happens, that there are many points, in the j omega axis, okay. All the points are mapped on the unit circle. So it is what? It is actually not one to one. All the points on the j omega axis, you see the graph, graphically you can see that there are jet plane is this one, okay, this is the jet plane, okay. So sigma less than 0 are mapped inside the jet plane, inside the unit circle. Sigma greater than 0 right side, all the points are mapped outside the unit circle, and j omega axis is mapped onto the unit circle. Okay. So this mapping j omega is what? It is the frequency, that is analog frequency or continuous frequency, and these are mapped onto the digital frequency omega. And what is the range of omega? Omega range is minus pi to plus pi. Okay. So you see I have written in the right side that omega ranges from minus pi to plus pi. In place of omega, we write omega into t, omega into t. So that is the analog frequency, continuous frequency, capital omega into t. Now, if you uh, find that you will find that this capital omega ranges from minus pi by t to plus pi by t. Okay. So the points in the continuous frequency range, or the frequencies lying in this range minus pi by t to plus pi by t, are mapped into the frequency range, digital frequency range minus pi to plus pi. Okay. Similarly, if we slightly change the axis of the continuous frequency range, that is pi by t to 3 pi by t. Okay, this range pi by t to 3 pi by t. These are also mapped. These are also mapped into the same frequency range minus pi to plus pi, because this rotor rotates within this angle minus pi to plus pi. Similarly, minus pi by t to plus minus 3 pi by t. These are also mapped within this frequency range minus pi to plus pi. So all the points are, so this mapping, different mapping from the points from S plane to Z plane are not one to one, they are many to one. There is many frequencies corresponds to many analog frequencies corresponds to one particular digital frequency. Okay, so this is one severe drawback, because when we go for higher frequency, then also they are mapped to lower frequency. Okay, higher frequencies are also mapped to lower frequency. So this actually you see that if you go above the axis of j omega at the beyond this pi by t, the frequency increases. So the high frequency points are also mapped to the low frequency points. This is nothing but aliasing effect. High frequency components are converted to low frequency components. So this is one drawback for this impulse invariance method. Now, whatever it is, so due to that, some limitation is there. Okay, I will discuss that in the later part of this topic. That to see the effect of the impulse invariance design method, let us express Hs in partial fraction form. So partial, so what we are, or what is our purpose? Our purpose is to convert the analog filter to digital filter. Analog filter transfer function is HAS. We have to convert it into HZ. So HAS is given by summation Ck divided by S minus Pk, that is sum of different partial fraction parts, that is we have different distinct poles Ck by S minus Pk, and different poles are there at pole locations Pk, and n number of such poles are there. Now if you take the inverse Laplace transform, okay, then according to the formula, that if it is 1 by S minus A, so it is e to the power at. Okay. 1 by S minus A in frequency domain, in time domain it is e to the power at. So that is done here, that in time domain there is also the different poles and the inverse. So different poles are there, so different corresponding inverse Laplace transform term will be there. So these are given by k is equal to 1 to n Ck into e to the power pkt. So now we sample. So this is the analog impulse response. Now you have to convert it into digital frequency response, impulse response. So how you convert? You have to sample it at some specific instance, that is t is equal to nt. So in place of t we write nt, and so we get this is hn or hant, same thing, it is quantized version. So it is k is equal to 1 to n Ck to the power pktn. Okay. So this actually Hn. Okay. So considering different poles. So we are considering only the poles here. Now Hz. Hz is what? Is the Z transform of Hn. Hn is calculated in this way. So just put Hn over there. So we get summation of summation k is equal to 1 to n ck to the power pk tn whole into z to the power minus n. So ck comes out, it is because it is a coefficient or constant, and summation e to the power pk t z inverse to the power n. Okay. So both z inverse is taken into the bracket, z inverse and e to the power pk t kept under the bracket of n, power of n. So now this forms one series, and this series can be written as 1 by 1 minus this to the power pkt z inverse as long as pk is less than 0. Okay, that means it should not be infinite. Okay, so to have finite value of the series, okay, pk should be less than 0. So uh, here inner sum converges because pk, that is left up poles, the left up points, the poles in the left up is plane. Okay, so here we can write this way, and we can write Az is equal to ck divided by 1 minus pkt z inverse. So final this is the final expression, system function of the digital filter. Okay. So some observations are there. We observe that the digital filter has poles at zk e to the power pkt because e to the power st is there. Z is equal to e to the power st. Okay, z is equal to e to the power st. So in place of s, we write s in time s domain or continuous or analog domain. S represents particularly the pole or pk, okay, poles in the left half s plane. Now uh, this in z domain, this poles becomes e to the power of that value pkt, that is t is the sampling interval. Now in this method only poles are mapped, okay, by z is equal to e to the power pkt, not zeros. Okay. If it is only zeros in the system function, then it would be FIR filters, but we are discussing IIR filters. Okay. Design of IIR filter and converting the IIR analog filter to IIR digital filter. So we are considering the poles, okay, and impulse invariance method is applicable only for poles, not for zeros. So all the points are, so only the poles are mapped from S to Z, not zeros. Although we have started these examples with this one, that is, it consists of poles only. Okay, but since this impulse invariance method deals with only the poles, okay, it is best understood by the use of poles. Okay, so we cannot map the zeros, okay, in using this method, impulse invariance method. Zeros from S plane to Z plane, we cannot map it. So that is written that only distinct poles have been considered, not multiple order poles. This is another drawback. So now, due to the presence of aliasing, this method is appropriate for low pass and limited class of band pass filters only. And this is unsuccessful for high pass filters. Okay. So because aliasing, that high frequency component will be treated as low frequency component. So in case of high pass filter, you have to deal with high frequencies. So you cannot design the high pass filter using this method, impulse invariance method, only limited to low pass and certain stage of band pass. Because band pass start with low frequencies components and ends with high frequency component. So that's why it is band pass, but very limited to low frequencies only. Okay. So in the low frequency range, the band pass filter can be designed, but not high frequency range. This is the drawback of impulse response method. Now, in summary, how we will design the impulse or the filter. So first step is get the analog filter transfer function HS. Okay. Then select T, that is sampling interval. Okay. Sampling interval should be mentioned. And once you find the poles pk, okay, from the inverse Laplace transform of HS using partial fraction method, and also distinct poles, not multiple order poles. Okay, complex conjugate poles can be implemented. Okay, but this method is actually, so once you get the poles pk, then just use this formula directly. Okay, that is summation ck divided by 1 minus pk tz inverse. They will get the direct digital transfer function of the corresponding analog filter. Okay. So now let us see some example. Okay, here I have mentioned some practice problem. Okay, you just go through it. I have given the solution also. Last time, one of your senior, no, this was actually given in book. I have given the solutions. Okay. So, so you just go through it. I am just showing you. Okay. So first problem, the same problem is written here. Are you seeing? Are you listening to the problem? Are you seeing the problem?
Yes, sir.
Okay. So first problem is, for the analog transfer function Hs 2 by s plus 1 into s plus 2, determine Hz using impulse invariance method. Assume t is equal to 1 second. Okay. So I will convert this filter Hs to analog filter to digital filter transfer function. So Hs is equal to 2 by this. So it is in general form. You have to convert it into partial fraction form. So it is done so this way, that a by s plus 1 plus b by s plus 2. So you get the coefficients a and b, that is ck actually. So both are 2, these are 2 and minus 2, and poles are located at minus 1 and minus 2. So according to the formula, that Hz is equal to summation ck divided by 1 minus pkt into z inverse. Just in place of pk, the poles, okay, in place of pk of the, in place of pk, you just put the values, both the two values, minus 1 and minus 2. With this, there are two poles located at minus 1 and minus 2. So you write those two values. So Hz will be what? That is 2 by 1 minus e to the power minus t, pkt. So pk in one case it is minus 1, okay, and in another case it is minus 2. So and their coefficients c1 and c2, that's our a and that are a and b, okay. So 2 and minus 2 are there. So it is 2 by 1 minus e to the power minus tz inverse minus 2 by 1 minus to the power minus 2 tz inverse. So just arranging it, okay, write the values of E, just arrange it and write in proper form, okay. So your final transfer function becomes 0.465 z inverse divided by 1 minus 0.503 z inverse plus 0.04976 z to the power minus 2, okay. Is it clear?
Yes, sir.
Okay. Then next problem, the same method, that using impulse invariance method with t is equal to 1 second, determine Hz, Hz if Hs is equal to 1 by s square plus root 2s plus 1. Okay. So, uh, so what should be the first step? First step is to find the poles. Okay. How will find the poles? You can find the poles, okay, from here, or you can use some other method, okay, by some empirical formula, okay, well known formula of inverse Laplace transform. Okay, here some another method is shown, that ht is directly calculated, okay, that is coming to be root 2 e to the power minus t by root 2 sine t by root 2. ht is calculated, okay, then in place of t is equal to nt, okay, as t is equal to nt, just sampling it. So and t is equal to 1 second, okay, so it becomes this one. So this is hn. Now you write a can calculate hz from here, okay. So hz, so z z transform of hn, it is actually this one, okay. hn इसका z ट्रांसफॉर्म करोगे तो ये फॉर्मूला यूज करो, फॉर्मूला से ये मिल जाएगा। और दूसरा तरीका भी है, अगर तुम अगर रूट्स पता चल जाएगा पोल्स, ओके, जैसे दिस ये मेथड में है। Design a third order Butterworth digital filter using impulse invariance technique. Assume sampling period t is equal to 1 second. Okay. तो इसमें देखो कैसे कर रहे हैं, यहाँ पे बता दिया है ट्रांसफर फंक्शन पहले से। थर्ड बटरवर्थ फिल्टर यूज किया है, बटरवर्थ फिल्टर में डिजिटल एनालॉग फॉर्म में है। थर्ड ऑर्डर बटरवर्थ फिल्टर का ये ट्रांसफर फंक्शन है, दैट इज 1 बाई s प्लस 1 इंटू s स्क्वायर प्लस s प्लस 1. So if you make it into partial fraction form, it is coming to be a by s plus 1 plus b by s plus 0.5 j into 0.866 plus c by s plus 0.5 minus a, complex conjugate pole है। So b और c भी complex conjugate होगा, b और c का वैल्यू यहाँ पे देखो, ये complex conjugate होता है। अगर पोल्स कॉम्प्लेक्स कंजुगेट है तो उसका कोफिशिएंट भी कॉम्प्लेक्स कंजुगेट होगा। जैसे ए का वैल्यू कैलकुलेट किया है, b का वैल्यू भी कैलकुलेट किया है पार्शियल फ्रैक्शन मेथड से, c डायरेक्ट b से मिल जा रहा है क्योंकि जस्ट इमेजिनरी पार्ट को नेगेटिव कर दोगे वो कॉम्प्लेक्स कंजुगेट हो जाएगा और कोएफिशिएंट मिल जाएगा। अब HS is now written, now use the impedance invariant technique that once HS is given in this form, HS अगर ये फॉर्म में है तब पार्शियल फ्रैक्शन का फॉर्म में है तब वो फॉर्मूला अप्लाई करना है, दैट इज CK summation of CK by 1 minus e to the power PKT Z इनवर्स। प्रीवियस केस में ये पार्शियल फ्रैक्शन में नहीं है, ये जो है पार्शियल फ्रैक्शन में नहीं है प्रीवियस केस, इसको तुम कर सकते हो पार्शियल फ्रैक्शन में लेकिन डायरेक्ट भी कर सकते हो। तो क्या होगा इसमें EZ PK you have already have the value of PK. PK is minus 0.5 minus J 0.866, one case minus 1, this one and this one. So all three will be again used, and just put this according to this formula, you just write and finally you can get the formula in terms of Z. Okay, you can get the impulse response in terms of Z. So this is the method. So next class tomorrow I will discuss another very important method, that is bilinear transformation. And you have to give me some extra class. Okay. So today are you free in the next half 5:30?